Google Deepmind is a world leader in AI technologies, having created systems with massive scientific potential. In the future, these AIs will be able to solve complex problems without being taught, and now we have the opportunity to learn from someone at the forefront of this development. Teddy Collins works on special research and strategy projects. The neural network Deepmind development has outstripped its competitors, defeating the most powerful computer programs in chess, Go and shogi, as well as some human grandmasters. Something you may not know is that Google Deepmind have also created an AI that learned how to walk without human help, a staggering achievement. So without further ado, please welcome Teddy Collins on how humans should interact in a world of machines.
Okay, so I will be talking about artificial intelligence, overfitting, and life. Does anyone know what the word overfitting means in the context of AI? Okay, so this will be a good lesson. Everyone will come out of this having learned one AI vocab word. Raise your hands if you've heard of machine learning. Okay, great. So an alternative title that would have worked for this would be What We Can Learn from Machine Learning. So before we get into that, a little bit of background. Who am I and why am I here? And this maybe has a little bit more relevance to me than to other people, because as you may have noticed, most of the speakers here are sort of very accomplished, impressive individuals who have done things in their lives, and I'm sort of like a random young person who's been thrown into the mix. And so this is a little bit of a mystery, like how did I end up on the stage? And the answer to this is that I am not here representing myself, but I'm here representing a company. And that company is an artificial intelligence lab called Deepmind. Raise your hands if you've heard of Deepmind. Okay, great. So for those of you who haven't, don't worry, I will explain what Deepmind is and what we do and sort of how it's relevant to the rest of the talk. So this is our logo. So what is Deepmind? Deepmind, much like many of you, is young and ambitious, and it's trying to do something that has never been done before. Specifically, for us, I'll talk about our history a little bit, and then I'll sort of get into the mission. So Deepmind was founded in 2010 by 3 people, Demis Hassabis, Shane Legg, and Mustafa Suleiman. Demis Hassabis is my boss and is probably the most brilliant person who I've ever met. I'll get a little bit later on in the talk into some of his prior accomplishments. And so in 2010, now you may have seen a lot about artificial intelligence in the news. It's sort of like a very hot area in tech, a lot of big breakthroughs. In 2010, this was not the case. It was almost impossible for Demis, Shane, and Mustafa to get funding for something that was AI. People thought it was sort of science fiction. But they were very good at their jobs. They managed to get funding from sort of some of the top players out there. And Deepmind grew and grew and had some research successes. And in 2014, it was acquired by Google in what was Google's largest European acquisition ever. And the company has kept growing, and today it has hundreds of scientists. There are about 700 people at Deepmind now, working on some huge breakthroughs, a few of which I'll talk about today, many of which I don't have time to get into, but if anyone has questions about more of the stuff we've done, I'm happy to get into details later. And so that's a bit of the history, but I think a more efficient way of learning sort of what is it that Deepmind is about is to talk about our mission statement. So we have a 2-part mission statement. Step 1 is to solve intelligence. And step 2 is to use intelligence to solve everything else. So we like to keep things very simple and concise. The solve intelligence side of things, what this means is that we do fundamental research into how to create the most general purpose artificial intelligence that can function as well as possible in the widest possible variety of domains, much like humans do. And this involves a combination of mathematics and neuroscience and statistics and every now and then some philosophy. And so at Deepmind, we have people coming together every day to sort of work on those questions. And the exciting thing about this, in addition to being this, engaging with this age-old, fascinating philosophical question, is that there are also an unlimited number of applications that you can imagine. I mean, if you think right now sort of what you think that the number one problem facing the world is, I guarantee that this is something that AI could help us solve. And so part 2 of our mission statement is, as we work on solving intelligence, we then want to harness some of this to solve the problems that the world is facing. And so that could be almost anything. And if you think about intelligence is sort of the most versatile, powerful tool that exists in the world. It has built sort of everything around you that separates us from the animal kingdom. You know, buildings and heating and air conditioning and movies and music and civilization and going to the moon and all of the technology that Big Shaq uses to make all of his music, right? Everything that you can imagine sort of flowed from intelligence. And so if you had an unlimited amount of intelligence that you could sort of funnel towards various projects, this would be like a huge accomplishment for humankind. So we'll get into some of the applications later on, but for now I'll begin by sort of talking about what it is that machine learning is and means. One final note about Deepmind first, which is that we see ourselves fundamentally as being an Apollo program for AI. And so we're not trying to build a particular product, we're not driven by profit. What we're trying to do is we're trying to tackle sort of one of the great questions of history, and hopefully that is something that will come with many scientific breakthroughs. Okay, so that's what Deepmind is. Now we can talk a little bit about what machine learning is and what it can do. So I will give a very quick overview of reinforcement learning, which is one specific subset of machine learning that we use a lot at Deepmind. So the idea is pretty straightforward. You have an algorithm or a program which we call an agent. You have an environment that it sits in. For us, this is often a game. And the agent looks at the environment, and then, based on what it sees, it takes some action. So this is like you just, like every day, right? You see food or something, and you take the food, and you're trying to maximize some reward signal, in this case, trying to be less hungry. And so you take an action, and then you learn from that, like what actions work well and what actions don't. And this sounds very intuitive, but this actually kind of runs against the grain of how most traditional programming works. So if we think a little bit about what is it that goes into these agents. With traditional programming, everything is handcrafted. So those of you, have any of you done sort of any programming in school? Raise your hands if you've done programming. Okay, great. So then you know that the normal form that programs take is that you specify quite specifically what it is that you want them to do in what kinds of circumstance, right? So classic sort of programming conceit is if-then, right? If you encounter this situation, then you do that. And machine learning kind of throws all of that out the window, and it says, we should create programs that actually don't know anything. They're kind of born with no knowledge. But they have the ability, much like a human child, to learn. And so they observe their environment, they do some experimenting, and they figure out what works and what doesn't work, and they take actions, and then over time, they develop a sense of what's good. Traditional programming is very specific. Specificity is kind of the happy place for normal programming. In the case of machine learning, you actually want to go as general as possible. The kind of one of the big aims of machine learning is to create a general intelligence, something that can function in all variety of domains. Traditional programming leans heavily on stuff being logic-based. In machine learning, especially the kind that we do, it's grounded. What that means is that you get sensory input. So for instance, if you're playing a computer game, you get the pixels of the game. And then you take actions based on that, as opposed to kind of being given these decision trees. And traditional programming is passive, whereas in this case it's active. That's like what I was talking about before. You're basically, these agents are mini scientists. So they're thrust into these worlds, and then they take actions, and based on the feedback they get from those actions, they develop a model of how the world works and what they need to do in order to get what they want. So if we go back now to the other half of this reinforcement learning diagram, that's kind of what's happening on the agent side. And on the environment side, one thing that Deepmind really innovated was the use of games, largely computer games, to train agents. These are really nice environments because they have a nice reward signal and because they were crafted specifically for humans to find them challenging. So we know that this is sort of a difficult thing. And you can slowly increase the complexity of the environments that you put these agents in. And so some of the early work that we did was using the Atari games. Is anyone here old enough to have played the Atari games? Yeah, okay, thank goodness. So the Atari games are classic games from several decades ago, and they're a good bit simpler than most of the games that people play today, and this makes them kind of a good first stop for teaching these agents, for putting these agents in environments and testing them. And so Breakout, this is one famous Atari game, and so the way this works from the perspective of the agent is the agent is kind of like born into the world, again, knowing nothing. It's like you're a baby and instantly you're just plugged into this bizarre Atari world. This is all you know. And you just see these pixels, and all you can do is you have controls to move the bat at the bottom of the screen. And so I'll give you one example of sort of what does it look like to see an agent learning this stuff. It's pretty cool. So early on, it's not very good. It kind of every now and then moves the bat to get to the ball, but I'm terrible at this game. I played it like 3 times. That is worse than me. After 300 games, it's better than me. So it gets the general principle that you want to move the bat back and forth. It's pretty rare now for the ball to get by it. And again, this is with no instruction. But then something sort of quite interesting happens after 500 games. So this is a trick that it learned how to do, and people who have experience playing the Atari games will know that apparently this is a trick that people figured out like several decades ago when the Atari games were big. But interestingly, the programmers who made this were not Atari experts, and they didn't know this. So the program learned something that was beyond their knowledge. And that is one of the really powerful things about machine learning. And that's sort of the theme of what I'm going to talk to you about today is how can we emulate that same creative drive and sort of adaptability in our own lives. So that's kind of the first example. The second example that I'm going to give you of what machine learning has done, again in the context of games, is Alphago. Alphago is probably the thing that Deepmind is most famous for. And it is a program that plays the game of Go. Go is sometimes described as the Asian equivalent of chess. Does anyone here play Go? Yes, great. Okay, we have a Go player. So, for everyone else, here's how it works. You have a board. It is a 19 by 19 grid. Players alternate turns placing a white stone and a black stone and a white stone and a black stone. And you can put the stone anywhere you want. The goal is that by the end, you essentially want to have surrounded like as much territory as possible. And so the rules are quite simple. Like they're much simpler than the rules of chess. But the game, interestingly, ends up being much more complex. So every talk today has an interactive element, and I've noticed that the interactive elements thus far have been quite fun. So I decided to make this what everyone wants to do on a Sunday, and the interactive element for my talk is going to be everyone's going to do some maths. So here is the question. For this board, how many possible board positions are there? Like how many configurations of white stones and black stones and blank spaces can you have on this 19 by 19 grid? As a reminder, this is what it looks like. So split into your teams, and you have 5 minutes. And don't Google this, by the way. Okay, you have to figure it out. Okay. Okay, who wants to volunteer an answer for how many possible board states there are? Yes? 361 factorial. That is not correct, but that may be... It's not 361 factorial, it is 3 to the power of 361, because each sort of vertex can be white, black, or blank. But I don't know which, off the top of my head, which number is actually bigger. Probably, actually it has to be 361 factorial. Yeah, I lied. Any other guesses? Yes, go ahead. Sorry? Can someone just yell it? 50 million. Okay, all right. That is on the lower side of what this number is. It's actually much lower than that. 2 to the power of 361. That would have been correct, except that you can have a blank space, so it's 3 to the power of 361. But you were both kind of on the right page. So how big is that number? Like, what does this number look like? That is roughly equivalent to 10 to the power of 170. Which, by the way, looks like this. Okay, that is how many possible board states there are in Go. And to put this in context a little bit, does anyone know roughly how many atoms there are in the universe? Yes, we have some hands back here. Sorry? Yes, 10 to the 80, that is correct. So, there are more possible board states in Go than there are atoms in the universe. And in fact, who knows very quickly, what would 10 to the 80 squared be? Yes, good, 10 to the power of 160. So what that means is that even if every atom in our universe were its own universe, each one containing as many atoms as our universe has, right? Then you would have 10 to the 160, which is still a billionfold less than the number of possible board states in Go. So it is, this game has sort of this overwhelming complexity. And the reason why this is relevant for machine learning is that this means that it is so complex that it is impossible, it's computationally intractable to try and tackle it the way people had tackled previous games like chess, right? So chess is something that is right on the cusp where it's very complex, but in the 1990s, there was this program, Deep Blue, which involved sort of a lot of very good chess players and a lot of very good engineers sitting down and writing down a lot of chess strategies. And if you calculated enough board positions, then you would kind of brute force your way to determining what a good move is in any given situation. With Go, this is totally out the window. It's impossible. And so this is why this has been this long-standing holy grail in the world of artificial intelligence. Just a few years ago, people thought that it was impossible to create what's called an evaluation function. An evaluation function is something that tells you what the relative likelihood of one person versus another person winning is, and that a competent AI Go player was at least a decade away. So at Deepmind, we see this as an invitation. This is sort of like a challenge that people are very ready to accept. So we put some of our best scientists on this project, and they built something that used this sort of new architecture. It combined two different neural networks, and we thought it was quite good, and we played against the European champion of Go, and it won, which was quite a big event, but you haven't really done it until you've played the world champion. And so in 2016, there was this momentous event where there was this challenge match in which Alphago, which was the Deepmind program, played Lee Sedol, who my boss describes as being the Roger Federer of Go. He's sort of been like at the top of the game for a decade, and he's very versatile, and he's a complete legend. And so this match took place, and it is difficult to describe just how manic this whole thing was. This is actually my first week at Deepmind, was the week that this happened. And it was complete insanity. Sometimes, I said earlier, this is called the Asian version of chess, but it's actually much more than that because the cultural significance far exceeds chess in the West. It's kind of like if you took chess, football, and philosophy and poetry and kind of rammed them all together into one thing. And so you can see from these photos of the team in Korea, I mean, these enormous screens outside, right, that you would normally see displaying say, massive world news, are displaying the positions that are unfolding in these Go games. Hundreds and hundreds of journalists who would mob all of the programmers whenever they kind of left their hotel rooms. There's our CEO, Demis, at the top left with Lee Sedol. So this was this enormous event. 200 million people watched it. So that's what the population of the UK is, like 70 million, something like that. Yeah, so this is roughly 3 times all of the UK tuned in to watch a board game. It's pretty phenomenal. It ended well. Alphago won. This is something ahead of this. People thought there was no way that this could happen, that without a doubt, Go is so complex that a computer cannot beat a human. But it won 4-1, and it was called a decade before its time. There's a funny story about this quote, by the way, which is apparently this comes from someone who said shortly before Alphago that having a competent AI Go player was a decade away, and everyone ridiculed him because they said there's no way this will be here in a decade, like you're way off mark. And then as soon as this happened, everyone ridiculed him for thinking it was a decade away. So it's like this guy just can't win. And so more significant than the actual victory, I think, is the nature of the victory. And this gets back a little bit to what I was trying to illustrate with the Atari example. So the most momentous instant in this match happened, it's move 37 of game 2, and you can see this triangle here, and that is the move that Alphago played. And I'm not very good at Go, but people who are great at Go have these incredible reactions to seeing this move played. So when it was played, everyone thought this was like a glitch. Essentially, this early in the game, it's very rare to play something on the fifth line, so this far towards the middle of the board. It's much more normal to play something on the third or fourth line. The idea being that you kind of want to control the territory that's near the edge, and then as the game goes on, you move towards the center. But Alphago played on the fifth line. People thought that this was a huge mistake. Many moves later, it turned out that there is this other area of the board, and this whole fight unfolded there, and this ended up kind of cascading into there, and move 37 was perfectly positioned to sort of pick up and finish out like the strategy of that particular play. And it required this incredible foresight, and as a result, this is considered to be this beautiful move that violated millennia of traditionally held Go wisdom. Like, people cry when they look at this move. A woman got a tattoo of this move. This is like apparently this totally mind-blowing thing. And what's so wonderful about this, and the reason why this is so significant and why this kind of encapsulates what is so magical about machine learning, is that nobody told Alphago to do this. No one taught it this. It didn't have this saved somewhere, right? This is sort of like the magic of machine learning. So how does it do this magic? It's not that it has some database of moves, because there are way too many moves to ever record in a database. It's not because humans who were experts programmed it with a bunch of strategies as worked with chess, because as we talked about, it's way too complex for that. It's not even necessarily because it had seen this previously in a game that it had played by itself. It's because it had, through playing lots of different games and experimenting with things in different settings and styles, and looking at different strategies, it learned a general intuition and principles that helped it make this decision in this unexpected moment. So I'm going to revisit the slide that we had earlier about the difference between sort of traditional programming and machine learning. And it's important here to talk about generality versus specificity, and machine learning really thrives with generality. So the magic of machine learning is that if you make things generally intelligent as opposed to specifically knowledgeable, they will surprise you. So it's a complete blank slate. You don't bias it with any of your own beliefs. You just let it experiment and allow it to learn. And eventually, it will learn things like move 37. And this is such a paradigm shift, because normally, in traditional programming, you think of trying to write something that's very specific and very specialized. But in this context, specialization is actually limiting. In terms of how this works, there's a whole lot of sort of technical wizardry that made Alphago possible that I'm not even capable of explaining. But since this is a generalist audience, I'd like to pull out one principle that I think is a useful kind of life idea. And that is something that is at the foundation of machine learning, and it has to do with the way these programs are trained. So with machine learning, you have training, you have testing. During training, you see all of these different possibilities. So in the case of Alphago, that means it's playing a lot of different Go games. The classic example, because the internet loves cats, is that you're trying to train something that can recognize images of cats and separate them from not cats. So the idea is you're going to give one of these things a whole bunch of pictures of cats and say these are cats, a whole bunch of pictures of not cats and say these are not cats, and then eventually it learns what a cat is. But what is very, very, very important is that you have to give it a set of training examples that are diverse and that represent like the entire possible space. And this is the number one pitfall that people usually run into. If you try to train something to recognize cats and you only give it pictures of black cats, and then you show it during the testing phase in the real world, a white cat, it won't recognize it as a cat. There's a famous story that apparently might not actually be true, but it's always told in machine learning circles, of the Pentagon, the US military, trying to develop a system to identify tanks. And so they trained it on a whole bunch of pictures of tanks and said, these are tanks, and a whole bunch of pictures of other things and said, these are not tanks. And it worked great. And then they took it out into the real world, and it completely failed. And it turned out it was because they took all of the photos of tanks on one day, and it was sunny, and all of the photos of not tanks on another day, and it wasn't sunny. And so all it learned was to identify whether there was sun. And so it ended up being totally useless. And what this is called, and this goes back to the word I used at the very beginning, is this is called overfitting. If you have examples that aren't diverse enough, then you will end up, your algorithm will overfit on those, and it won't learn the thing that you're actually trying to learn. And so this is like the number one, the cardinal sin of machine learning is overfitting. And when you take a course in machine learning, like what everyone will tell you is don't overfit. The number one most important thing is don't overfit. Make sure your training data is varied enough. In the case of reinforcement learning, like Alphago, it has to do with this question of exploration, exploitation. Make sure that you're exploring enough so that you have a good sense holistically of this space. if you do that, then you can have these incredible insights like the ones that we've been looking at. And in my opinion, this is such a cool idea because it doesn't only apply to programs, but I think this also applies to people. And this has been something that has very much resonated with my life, and also I think with the lives of a lot of the people who I respect the most. So in my case, I ended up doing a whole bunch of very random, eclectic stuff before I wound up working in AI. So when I was a kid, I was really into maths, and then I got bored of that, and in uni I studied politics, and I worked in finance for a while, and then sort of got very disillusioned with that, and then I worked on a book with a professor of mine, and then I got disillusioned with that, and so I studied philosophy, and somehow now I work in AI. And this is a mystery to everyone I know. But this happened, and strangely enough, I actually would not be able to do my job now had I not done all of these things. And I had no idea at the time that these would lead to this. This is I think people talk about this a lot, is that things are very clear in retrospect, but often very unclear at the time. But this was sort of, for me, it was about exploring this space in full and having sort of diverse training examples. A much more impressive version of this is my boss, Demis, who I mentioned before as kind of the most brilliant person who I've met. And he founded Deepmind. He was one of the co-founders. His path to that was also quite varied. So he was a child chess prodigy. He then stopped playing chess competitively and wrote the award-winning game Theme Park in the 90s. This is actually before he went to university. Then he went to university, he studied computer science. Then he started a games company. After the games company, he got a PhD in neuroscience, and then he ended up in AI. And so again, this is the kind of thing that no one could have charted this. And the point I'm trying to get at is that it's a little bit like programming. This is a bit of a stretch, but the idea is no one could have written down the precise instructions for this. Just like you cannot write down the precise instructions to tackle really complex domains, such as Go. And this, I think, is something that you really can, this is what we can learn from machine learning, is that overfitting is bad. It's bad for programs and it's bad for people. So what I remember so clearly from being the age of the younger people in this audience was being so terrified that I had to choose a particular thing to do. Right? And people said, okay, well, you go to university, you have to choose what you're studying in university, and then that leads you to this career, and so you have to follow these steps, and stop doing sort of frivolous things on the side, right? Like, don't take this random trip somewhere, or study this language that's unclear how that will be useful, or, take this random course, or do this random summer internship. And actually, something we've learned from machine learning is that randomness is great. Randomness and random exploration are how you end up exploring the space of possibilities to the point that you can then improvise when you reach unexpected complex domains. And so I right now have what I consider to be my dream job. And it's a job that didn't exist 10 years ago when I was your age. And it's entirely possible that your dream jobs don't exist now and that you'll find them in 10 years after a whole bunch of random exploration. And so a way of thinking about this would be to say that if the past was chess, which is to say it's something that is difficult, but you can just barely brute force it, right? Like the world was always a complicated place to make your way in, but there was enough continuity that you could do that. It's becoming a less predictable and in many ways more exciting place. Like the future is Go. And if you want to begin to build the skills that are the most helpful for navigating that, I would encourage trying as many random things as possible, and don't feel like you have to be able to explain to someone how these will all connect into one given output. And so that's sort of the main message, but I just want to finish by coming back briefly to the Alphago story. So you saw this amazing move in game 2. In game 4, Alphago was winning, and then Lee Sedol played this move, where the triangle is there, which was equally mind-blowing. And something that, again, people were confused as to, does this make sense? Is this a mistake? It turned out to be totally brilliant, and he actually won that game. And I think that means that he was the last person to ever beat Alphago. And he said later on that Alphago kind of pushed him to think about things in a new light, and that it had changed the game of Go, but it had also reinvigorated his passion for Go. So sometimes people look at something like Alphago and they say, this is about machines replacing humans. And that could not be further from the truth. What's happening now, and what machine learning is bringing us, is this incredible symbiosis, which is this age of humans and machines collaborating on things, and as a result, having all of these amazing new discoveries in domains that range from Go to the sciences to economics. And it is exactly this kind of symbiosis that I think is going to create the jobs that don't exist now, but will exist in 10 years, that you will all do like an incredible job of finding and executing. And there are so many applications beyond games. Games I've used as the examples here because it's a really useful training platform. But to go back to the Deepmind mission statements, Poet 2 is use this to solve everything else. And this is just a random sampling of, again, I would encourage you to think of anything that you think is a problem in the world, anything that you want to try and tackle. AI can help humans tackle that. And it will be this kind of interactive, sort of symbiotic problem solving. So that is all of the content. As a lesson recap, for the young people, don't overfit. For the older people, please keep employing people like me who do random stuff and have like no area of specialization. I would feel immensely guilty if the people in this room followed my advice and then didn't get a job because of it. And to everyone, look forward to an incredible future because this is going to be great for humanity. So, thank you very much.
When it comes to machine ethics, are you worried that when we ask a question, if we ask an artificial intelligence to do something a bit more important than just play a game, so, for example, pure world hunger, and then you give an artificial general intelligence that task, are you worried that it might solve that in an unpredictable way that wasn't intentional?
If you give an AI program one of these one of these big problems that I said it could help solve, but if it's a kind of vaguely formulated problem, could it end up technically solving the problem but doing it in a way that you didn't want? This is something that a lot of people have been thinking about and writing about, and this is one reason why Deepmind does a lot of research into the field of technical safety, which is about trying to ensure that before you ask it a question like that, you have some pretty good guarantees about how it will behave, and so that you can build in the kind of safeguards that humans have automatically, right? There are lots of things that humans ethically take for granted, and so there are compromises that they wouldn't make that people sometimes worry about machines making. The good news is we're a ways off from giving it anything that is that sort of vague and nebulous, and that I'm quite optimistic that safety research will continue progressing alongside like the capabilities of AI, such that long enough before we get to the point of asking it to do something that consequential, we have become very comfortable with the knowledge that it will do it in a safe and ethical way. But these are exactly the kinds of questions that people need to be asking in the field.
Yeah. Next question.
Hello, I'm William. I have a question regarding research. I think you showed a slide showing the application of these things, and one thing that wasn't mentioned was the military. But more specifically, I want to ask, we're familiar with scientific endeavours, but obviously they came with a certain research grant, wherever that may be. And my concern is that perhaps the military, whether it be the MOD or the Pentagon, are the people committing the research funding, and therefore the avenue for AI, although it could be good in implication, may be narrowly focused on its military application.
Yeah, so this is another important ethical question. Generally speaking, sort of questions about ethics fall into two camps, and we kind of hit both of them. One is the camp of what if it does something you didn't expect, and the other is the camp of what if it's being used by a bad actor. So maybe the military is, well, whether it's bad or good is a question of opinion, but I think most people would think that it would be better for most of the research to go into stuff that is not zero-sum, like curing disease, than to go into developing weapons. And that's one reason why two of the co-founders of Deepmind have signed these public statements that are requesting that governments not use AI for things like autonomous weapons systems. We're really trying to set a good precedent in terms of the ethics discussions. And at the moment, AI is taking off very, very quickly, and it's still in the stage where these sort of ethical positions are being shaped, and we're doing our best to make sure that these are ethical positions that everyone can agree are right.
I think Vladimir Putin came out recently saying that whoever controlled AI would control the world. I'm interested to know what you think about that.
Yes.
And then secondly, I note that some other influential individuals like Elon Musk have argued quite persuasively that there should be a more open source and a more flat structure to AI, so that no one company, like Deepmind, for example, should have domain over that knowledge, and in that way we can reduce, some unexpected bad side effects. I'm interested to know what you think about both Vladimir's point and Elon's point.
Sure. So with respect to Putin, this kind of stuff is super worrying. I think that all AI scientists, are concerned about the idea that this stuff will be co-opted by great powers and just used for military applications. To the earlier question, that's why we're, trying our hardest to head things off before they go in that direction, right? To make sure that you can reach that global society reaches agreements about prioritizing, let's say, medical research over, say, autonomous weapons. In terms of the second one, we at Deepmind are hugely in support of openness. So, we publish our research, we open source code. One of the nice things about AI is that it is still quite an academic community. And so we've done a lot of collaboration with OpenAI, which is the nonprofit that Elon Musk set up. This is something that we also feel is very important. And we're doing our best to make sure that the work that we do can be shared such that it has the maximum positive impact possible. And it's very lucky that AI is such an academic domain, because there are lots of areas of industry and tech where that is not the standard. But luckily, because a lot of the people who come to work at Deepmind are still part-time professors or are still very much plugged into the academic world, there is the expectation that you will publish and that you will open source your code. And I think those are really good cultural norms to have set up in the industry.
Do you ever worry that the machines will rise?
I think that the traditional, it's definitely a good thing to have people thinking about technical safety questions and thinking about how could things go wrong so that we can head it off before that happens. We do a lot of technical safety research. I think that in terms of the classic sort of science fiction setup where one day you're playing Go and the next morning you wake up and some evil robot has taken over the world, I'm less concerned about that. But it is definitely good to have people overly cautious as opposed to under-cautious, and we try to be over-cautious.
Cool, thank you for the talk. You mentioned that Go is obviously a very complicated game, but one thing that is simple about it is that somebody wins and somebody loses at the end, which I guess is what you need to build the intelligence. How do you think about applying this in some fields where maybe what's good and what's bad isn't so obvious, so things like politics, business strategy perhaps, where good or bad is pretty badly defined?
So this is a big question in safety research, is how do you set the reward function is the thing that the agent is trying to maximize. How do you set a reward function in a domain that isn't as clear-cut as one of these games? And there's lots of interesting research going on there. One area that I personally find quite interesting is something called inverse reinforcement learning. In inverse reinforcement learning, the way it works is that you're given a whole bunch of, the agent is given a whole bunch of scenarios and is told what the human judgment was about which one was preferable. And then it learns the reward function from that. So often there are things that we might not be able to put an exact number on in terms of how good is this versus how good is that. But if you give us some options, we can easily say, well, this thing is clearly better than those things. And so with difficult to define reward functions such as that, inverse reinforcement learning is one promising path. That said, there are definitely a whole, when you get into things like politics, there are a whole host of stuff, of areas that are not as clear-cut and that are very subjective, where it's not necessarily the case that everyone will agree on these sorts of things. And this is why we try to be very cautious about where we apply things and not applying them in domains like that until we're really certain that they're going to do something that is incontrovertibly the right decision.
One last question, please.
I admire your passion for machines, but it does beg the question, what's the biggest flaw of humans? For you to go to love machines.
I think, this is a very good question. What's the biggest flaw of humans? Well, one thing is that we don't have enough time. We don't have enough time to solve all these problems. We have so much brain power amassed, right? But it's not enough. And it would be really, really nice if you could have something that could do all of the bits that you don't really have to want to spend time thinking about, and take that sort of off your plate so that we can do more fun things. But I guess I would, maybe it's a little bit of a cop-out, but I'd say that we don't have enough time.
The great thing then, and what a lot of them had in common, is beside imparting some knowledge and learning about the different subjects, they really had a couple of really simple core messages that would be very relevant for giving advice to young students or indeed more senior leaders about what careers to recommend for students going forward.